Hello and welcome back. So far we have understood theoretically how gradient descent works and stochastic gradient descent works. In scikit-learn we have got implementation for stochastic gradient descent in linear models. It is called as SGD regressor. This is for regression problems. For classification we have got SGD classifier. We will see that later. On SGD regressor we have got the hyperparameters like learning rate and learning schedule. We can play with those learning rate and learning schedule parameters and see how the model is working. Or we are trying to understand what is hyperparameter tuning in this class. This is an important concept. Hyperparameter tuning is the important concept in AI. When you look at deep learning models or when you are trying to play with deep learning models, hyperparameter tuning is the best thing, will give you the best models. So these are all the fundamentals for whatever we are going to encounter in this course in the coming classes. So let me try to execute this and import the modules. You see all the modules which you know already. Only the new module you see is new class you see is SGD regressor. So I am using the same salary data set and trying to apply SGD regressor and with grid set CV. Okay, hyperparameter tuning can be done very efficiently with grid set CV, and you can find best hyperparameters using grid set CV because it is the model selection approach we are going to use throughout the course. So I loaded the data and looked at the head, and I splitted the data into train test. We are doing this from the day one, right? The first step we need to do is train test split, and then I am doing the data pre-processing. All this code is from our previous classes. We actually did EDA, exploratory data analysis, and understood how exactly the data should be converted. So I have taken the simplest way of converting data here, right? Imputing the nulls with mode and then taking the negative values in the lines of code and trying to replace it with 0. So used the data pre-processing, and then I am splitting data into train X and train Y, and now I am going to use SGD, the stochastic gradient descent regressor to build model. We have seen that the gradient descent algorithm expects data in similar scale. All columns should be in similar scale, right? To achieve that, either you should be applying the standard scaling or min-max scaling or dividing by maximum number also. We are using standard scaling here. I hope you remember what is standard scaling. Standard scaling is nothing but subtracting mean of each column from itself, from the data points, and then dividing with the standard deviation. When we do standard scaling, there is no guarantee that all columns will come in the range of -1 to 1, but all the columns will come to some scale, similar scale. That is enough to get good accuracy on SGD regressor or the gradient descent algorithm. So we need to remember this. Before we apply the gradient descent algorithm, we should do standard scaling. I have taken the standard scalar class and then did fit transform on X-train. When I did fit transform X-train, when I did fit, it is going to take the means and standard deviations of all the columns in the dataset, and then when I say transform, that's when it's going to subtract mean and then divide with the standard deviation. If you have 20 columns in your dataset, there will be 20 means and 20 standard deviations. The first column's mean is going to be subtracted from first column and divided with its own standard deviation. Second column's mean subtracted from second column and divided with its own standard deviation. Like that, 20 operations will happen when you do the transform, or vectorized implementation will happen. Right? In a matrix manipulation, it actually subtracts scalar subtraction and scalar division it will do. I think you remember the concepts. Okay, so when I run this, the data becomes scaled. Now I can apply SGD regressor. As we have applied the linear regression algorithm, we need to create the class. It is similar to that. We created the class, and you remember the random state. It is 42. It's going to generate whatever the random variables it is generating. In SGD regressor, what is the random variable it is generating? The theta, initial theta, it's going to generate random, right? If you don't set the random state is equal to some number, any number can be chosen. 42 is not a constraint. Any number can be chosen. If you don't set this right, every time you execute, it is going to choose a different random theta, and the iterations may not be sufficient on the hyperparameters like learning rate may not actually make the algorithm converge to the global minima in the given iterations. So setting random state is always good on the SGD regression. I set random state and created the class, and then I am fitting. Right, the same thing we did in linear regression also. Linear regression dot fit, and then we passed x and y. Here we are passing the standardized x and the y, right? And then we are using the SGD, right? When you fit the model, it is going to take the random theta and then calculate the gradient by multiplying with alpha, the learning rate. It is going to subtract it from theta like that, and it's going to converge towards the global minima. All that happens when you do fit, right? Once it reaches the global minima, it has got the best thetas. Right? Now we can predict it. And while predicting also, you need to pass the standardized x only, because the understanding was made on the standardized x. Okay, so I passed and train predict I did, and then calculating the mean squared error and the R square score. For mean squared error, you need y and y cap both, because it is y minus y cap whole square divided by m sigma I is equal to 1 to m. And the R square score also needs RSS and TSS to calculate those. Also you need y and predicted value. Let us try to execute this and see. I have got 62% accuracy. Even on the linear regression model, we have got the same accuracy. By default, this stochastic gradient descent algorithm will have default values specified to the learning rate and the iterations. Let us see what those are. So these are called as hyperparameters. So if you look at the n iters, max iters, right? Max iters is 1000. By default, it is doing 1000 iterations. And then the learning rate, generally if you say constant, it takes eta 0 as the learning rate, or alpha. In our theory, we said the learning rate is as alpha, but here it is eta 0 in scikit-learn. So if you say constant, learning rate is equal to constant, whatever value you set to eta 0, it's going to be taken as learning rate. But if not, it is going to use learning schedule, right? Optimal, inverse scaling. These are all different approaches of calculating learning schedule. This is a stochastic gradient descent, so it is always suggested to put a learning schedule. But here I used default parameters and then tried to build a model, and it gave 62% accuracy. Let us try to play with the hyperparameters a little bit and see what happens. So by default, what is eta 0 here? Let us see. It is 0.01, right? So at 0.01, we have got 62% accuracy. So let me try to increase the value and see what happens. 0.1 is always greater than 0.01, right? And then reduce the number of iterations. What happens? Let us see. So it reduced the accuracy, reduced a little bit. Let me try to make this 10 iterations. See that it reached the global minima. So showing a warning saying that before it reached the global minima, it actually reached the maximum iterations. Okay. So if you increase this even more, what happens? Let us see. See that the accuracy, R square score actually gave a 0.44. That means 44%. If you increase more, the model is becoming worse, right? The model is becoming worse. If I give 1 here, and I have got 20% accuracy, right? So it is diverging. Actually, what is happening is the algorithm, instead of reaching the global minima, it would have started at some theta, and then it started diverging and went up, and we have got 20% accuracy. So when you started with some learning rate and you are not getting good accuracy, you need to increase the eta a little bit, eta 0 a little bit, and see what's happening, and decrease the eta 0 a little bit and see what's happening. Let me try to reduce this and see what happens, right? 0.001. See that it gave me negative R square score, right? That means it is still not reached. When alpha is too small, what happens? The step size will reduce, right? When I don't know whether you remember this or not. Let me open that PPT and show you. On the gradient descent, we understood that when the learning rate is too small, the convergence becomes very slow. When the learning rate is too high, the convergence becomes, it starts diverging. So we are in the second case, because when you played with those thetas, right, you understood. Okay, 0.01 is the best theta where you are reaching at, the 62% accuracy. And to apply it onto the test set, we need to apply all the transformations, and then we can use the same model to predict. We got 66% accuracy. But I said that we need to play with the learning rate a little bit and then understand the appropriate number, right? But it is always not possible, because the learning rate 0.0121 may be the best alpha or the learning rate. But if you have to find that exact number, it is humanly impossible. So we need to use model selection approach, the grid set CV. So let us try to understand how exactly we can choose the best parameter using grid set CV in the next coming class. Thank you.